Now the auxiliary equations v open brackets 1 minus x equals 0, v prime open brackets 1 minus z equals 0 give vx equals v prime z equals v prime. Substituting we have v prime equals v prime, therefore 0 equals 0. As an example of the latter case, let us take IO sig1, all uppercase, some y's are x's, all lowercase, vy equals vx, vy equals vx, all uppercase, some z's are not y's, all lowercase, v prime z equals v prime, open brackets, 1 minus y, close brackets. V prime open brackets 1 minus z close brackets equals v prime y, v prime open brackets 1 minus z close brackets equals v prime x. Now the auxiliary equations being v open brackets 1 minus x close brackets equals 0, v prime open brackets 1 minus z close brackets equals 0. The above reduces to v prime equals 0. It is to this form that all similar cases are reducible. Its interpretation is that the classes v and v prime have no common member, as is indeed evident. The above classification is purely founded on mathematical distinctions. We shall now inquire what is the logical division to which it corresponds. The lawful cases of the first class comprehend all those in which, from two universal premises, a universal conclusion may be drawn. We see that they include the premises of Barbara and Celant in the first figure, of Cesar and Camestres in the second, and of Bramantip and Camines in the fourth. The premises of Bramantip are included because they admit of a universal conclusion, although not in the same figure. The lawful cases of the second class are those in which a particular conclusion only is deducible from two universal premises. The lawful cases of the third class are those in which conclusion is deducible from two premises, one of which is universal and the other particular. The fourth class has no lawful cases. Among the cases in which no inference of any kind is possible, we find 6 in the fourth class distinguishable from any others by the circumstance that the result of elimination does not assume the form 0 equals 0. The cases are all uppercase, some y's are x's, some z's are not y's, some y's are not x's, some z's are not y's, some x's are y's, some z's are not y's, and the three others which are obtained by mutation of premises. It might be presumed that some logical peculiarity would be found to answer to the mathematical peculiarity which we have noticed, and in fact there exists a very remarkable one. If we examine each pair of premises in the above scheme, we shall find that there is virtually no middle term, i.e. no medium of comparison in any of them. Thus, in the first example, the individuals spoken of in the first premise are asserted to belong to the class uppercase y, but those spoken of in the second premise are virtually asserted to belong to the class not uppercase y. Nor can we by any lawful transformation or conversion alter this state of things. The comparison will still be made with the class uppercase y in one premise, and with the class not uppercase y in the other. Now in every case besides the above 6, there will be found a middle term, either expressed or implied. I select 2 of the most difficult cases. In AO, Fig 1 is all uppercase, all y's are x's, some z's are not y's, we have, by negative conversion of the first premise, all uppercase, all not x's are not y's, some z's are not y's, and the middle term is now seen to be not y. Again in EO, Fig 1, all uppercase, no y's are x's, some z's are not y's. Approved conversion of the first premise. See conversion of propositions. Gives all uppercase, all x's are not y's, some z's are not y's. And the middle term, the true medium of comparison, is plainly not y, although as the not y's in the one premise may be different from those in the other, no conclusion can be drawn. The mathematical conclusion in question, therefore, the irreducibility of the final equation to the form 0 equals 0, adequately represents the logical condition of there being no middle term or common medium of comparison in the given premises. I am not aware that the distinction occasioned by the presence or absence of a middle term, in the strict sense here understood, has been noticed by logicians before. The distinction, though real and deserving attention, is indeed by no means an obvious one, and it would have been unnoticed in the present instance but for the peculiarity of its mathematical expression. What appears to be novel in the above case is the proof of the existence of combinations of premises in which there is absolutely no medium of comparison. When such a medium of comparison, or true middle term, does exist, the condition that its quantification in both premises together shall exceed its quantification to a single whole has been ably and clearly seen by Professor de Morgan to be necessary to lawful inference. Cambridge Memoirs, Volume 8, Part 3. And this is undoubtedly the true principle of the syllogism, viewed from the standing point of arithmetic. I have said that it would be possible to impose conditions of interpretation which should restrict the rules of this calculus to the Aristotelian forms. Those conditions would be, first, that we should agree not to interpret the forms all lowercase v open brackets 1 minus x close brackets, v open brackets 1 minus z close brackets. Secondly, that we should agree to reject every interpretation in which the order of the terms should violate the Aristotelian rule. Or instead of the second condition, it might be agreed that, the conclusion being determined, the order of the premises should, if necessary, be changed so as to make the syllogism formal. From the general character of the system, it is indeed plain that it may be made to represent any conceivable scheme of logic by imposing the conditions proper to the case contemplated. We have found it, in a certain class of cases, to be necessary to replace the two equations expressive of universal propositions by their solutions, and it may be proper to remark that it would have been allowable in all instances to have done this, so that every case of the syllogism, without exception, might have been treated by equations comprised in the general forms, all lowercase, y equals vx, or y minus vx equals 0, a, y equals v open brackets 1 minus x close brackets, or y plus vx minus v equals 0, e, vy equals vx, vy minus vx equals 0, I, vy equals v open brackets 1 minus x, vy plus vx minus v equals 0, Footnote. It may be satisfactory to illustrate this statement by an example. In Barbara we should have all uppercase, all y's are x's, all lowercase, y equals vx, all uppercase, all z's are y's, all lowercase, z equals v prime y, z equals v prime x, therefore all uppercase, all z's are x's. Or we may multiply the resulting equation by 1 minus x, which gives all lowercase, z, open brackets 1 minus x, close brackets, equals 0. Whence the same y be the term to be eliminated and let x stand indifferently for either of the other symbols, then each of the equations with the premises of any given syllogism may be put in the form, all lowercase, ay plus bx equals 0, alpha, if the premise is affirmative and in the form ay plus b, open brackets, 1 minus x, close brackets, equals 0, beta. If it is negative, a and b being either constant or of the form plus or minus c. To prove this in detail, let us examine each kind of proposition, making y successively subject and predicate. A. All uppercase, all y's are x's, all lowercase, y minus bx equals 0, gamma. All uppercase, all x's are y's, all lowercase, x minus by equals 0, delta. E. All uppercase, no y's are x's, all lowercase, xy equals 0, all uppercase, no x's are y's, all lowercase, y minus b, open brackets, 1 minus x, close brackets, equals 0, epsilon. I. Some uppercase x's are y's, some y's are x's, all lowercase, bx minus by equals 0, zeta. O. All uppercase, some y's are not x's, all lowercase, vy minus c, open brackets, 1 minus x equals 0, beta. All uppercase, some x's are not y's, all lowercase, vx equals b, open brackets, 1 minus y, close brackets. Therefore, vy minus b, open brackets, 1 minus x, close brackets, equals 0, theta. The affirmative equations gamma, delta, and zeta belong to alpha, and the negative equations epsilon, eta, and theta to beta. It is seen that the two last negative equations are alike, but there is a difference of interpretation. In the former, all lowercase, v, open brackets, 1 minus x, equals some not uppercase x's. In the latter, all lowercase, v, open brackets, 1 minus x equals 0. The utility of the two general forms of reference, alpha and beta, will appear from the following application. First, a conclusion drawn from two affirmative propositions is itself affirmative. By alpha, we have for the given propositions all lowercase, ay plus bx equals 0, a prime y plus b prime z equals 0. And eliminating ab prime z minus a prime bx equals 0, which is of the form alpha. Hence, if there is a conclusion, it is affirmative. Second, a conclusion drawn from an affirmative and a negative proposition is negative. By alpha and beta, we have for the given propositions all lowercase, ay plus bx equals 0, a prime y plus b prime, open brackets, 1 minus z, close brackets, equals 0. Therefore, a prime bx minus ab prime, open brackets, 1 minus z, close brackets, equals 0, which is of the form beta. Hence the conclusion, if there is one, is negative. Third, a conclusion drawn from two negative premises will involve a negation, not uppercase x, not uppercase z, in both subject and predicate, and will therefore be inadmissible in the Aristotelian system, though just in itself. For the premises being all lowercase, ay plus b, open brackets, 1 minus x, close brackets, equals 0, a prime y plus b prime, open brackets, 1 minus z, close brackets, equals is only interpretable into a proposition that has a negation in each term. 4. Taking into account those syllogisms only, in which the conclusion is the most general that can be deduced from the premises. If, in an Aristotelian syllogism, the minor premises be changed in quality, from affirmative to negative or from negative to affirmative, whether it be changed in quantity or not, no conclusion will be deducible in the same figure. An Aristotelian proposition does not admit a term of the form not uppercase Z in the subject. Now on changing the quantity of the minor proposition of a syllogism, we transfer it from the general form, all lowercase a y plus b z equals 0, to the general form a prime y plus b prime open brackets 1 minus z close brackets equals 0. See alpha and beta or vice versa. And therefore in the equation of the conclusion there will be a change from z to 1 minus z or vice versa. But this is equivalent to the change of uppercase Z into not uppercase Z, or not uppercase Z into uppercase Z. Now the subject of the original conclusion must have involved an uppercase Z and not a not uppercase Z. Therefore the subject of the new conclusion will involve a not uppercase Z, and the conclusion will not be admissible in the Aristotelian forms except by conversion, which would render necessary a change of figure. Now the conclusion of this practice are always the most general that can be drawn, and therefore the above demonstration must not be supposed to extend to a syllogism in which a particular conclusion is deduced when a universal one is possible. This is the case with Brahmantic only, among the Aristotelian forms, and therefore the transformation of Brahmantic into Kamenis and vice versa is the case of restriction contemplated in the preliminary statement of the theorem. 5th. If to the minor premise of an Aristotelian syllogism we substitute its contradictory, no conclusion is deducible in the same figure. It is here only necessary to examine the case of Brahmantic, all the others being determined by the last proposition. When changing the minor of Brahmantic to its contradictory, we have AO, Fig. 4, and this admits of no legitimate inference. Hence the theorem is true without exception. Many of the general theorems may in like manner be proved. Under footnote. Perhaps the system we have actually employed is better as distinguishing the cases in which lowercase c only may be employed from those in which it must. But for the demonstration of certain general properties of the syllogism, the above system is, from its simplicity, and from the mutual analogy of its forms, very convenient. We shall apply it to the following theorem. Footnote. This elegant theorem was communicated by the Reverend Charles Boole, Fellow and Professor of Mathematics in Trinity College, Dublin, to whom the author desires further to record his grateful acknowledgement for a very judicious examination of the former portion of his work and for some new applications of the method. The following example of reduction ad impossible is among the number. Regisend mood barocco, all uppercase, all x's are y's, all lowercase, 1 minus y equals v prime, open brackets, 1 minus x, close brackets, all uppercase. Some z's are not y's, vz equals v, open brackets, 1 minus y, all uppercase. Some z's are not x's, all lowercase, vz equals v, v prime, open brackets, 1 minus x. Reduct mood Barbara, all uppercase, all x's are y's, all lowercase, 1 minus y equals v prime, open brackets, 1 minus x. All uppercase, all z's are x's, all lowercase, z, open brackets, 1 minus x, close brackets, equals 0, all uppercase, all z's are y's, all lowercase, z, open brackets, 1 minus y first members, by 1 minus y we obtain x open brackets 1 minus y close brackets equals 0. The equation from which we set out in the text as if the previous one is a solution. End of footnote. Given the three propositions of a syllogism, prove that there is but one order in which they can be legitimately arranged, and determine that order. All the forms above given for the expression of propositions are particular cases of the general form, all lowercase, a plus bx plus cy equals 0. Assume then for the premises of the given syllogism the equations, all lowercase, a plus bx plus cy equals 0, 18, a prime plus b prime z plus c prime y equals 0, 19. Then, eliminating y, we shall have for the conclusion, all lowercase, a c prime minus a prime c plus b c prime x minus b prime c z equals 0, 20. Now taking this as one of our premises, and either of the original equations, suppose 18 as the other if by elimination of a common term x between them, we can obtain a result equivalent to the remaining premise 19. It will appear that there are more than one order in which the propositions may be lawfully written, but if otherwise, one arrangement only is lawful. Effecting then the elimination, we have all lowercase, bc open brackets a prime plus b prime z plus c prime y close brackets equals 0, 21, which is equivalent to 19 multiplied by a factor of bc. Now on examining the value of this factor in the equations a, e, I, o, we find it in each case to be e or minus c. But it is evident that if an equation expressing a given proposition be multiplied by an extraneous factor derived from another equation, its interpretation will either be limited or rendered impossible. Thus there will either be no result at all, or the result will be a limitation of the remaining proposition. If, however, one of the original equations were all lowercase x equals y, or x minus y equals 0, the factor bc would be minus 1 and would not limit the interpretation of the other premise. Hence, if the first member of a syllogism should be understood to represent the double proposition all uppercase x are uppercase y's and all uppercase y's are uppercase x's, it would be indifferent in what order the remaining propositions were written. A more general form of the above investigation would be to express the premises by the equations, all lowercase, a plus bx plus cy plus bxy equals 0, 22, a prime plus b prime z plus c prime y plus b prime zy equals 0. After the double elimination of y and x, we should find all lowercase, open brackets, bc minus ad close brackets, open brackets, a prime plus b prime z plus c prime y plus b prime zy close brackets equals 0. And it would be seen that the factor bc minus ad must in every case either vanish or express a limitation of meaning. The determination of the order of the propositions